Hello Year 12 Chemistry students, this is Mr. Nicholson and today we are going to talk about addition polymerisation. This is the polymerisation process that occurs with monomers that contain a double bond. Now what we're going to do today is we are going to look at the addition polymerisation process in detail. This is the main process that is involved in the polymerisation of monomers that have a double bond as their functional group. And this is the process that is involved in the commercial polymerisation of most plastics that are made from petroleum. Now it occurs via two main ways, which is free radical polymerisation or via the use of a catalyst, specifically the ziegler-natta catalyst. And ziegler-natta, that's actually named after the scientists who developed the catalytic process to make this polymerisation method. The first polymerisation process that we are going to look at today is free radical polymerisation. This process has three key steps: initiation, propagation, and termination. Pictured on this slide is a diagram that represents the initiation step. Before we get into this, I just want to explain the key molecules that are involved in this step. First and foremost, free radical polymerisation is started and occurs via the use of what's known as a free radical. Now, a free radical is a chemical species that has one free electron in its outer valence shell. Now this is unusual because most atoms like to pair up electrons in their outer shell. Alright, an example of that would be oxygen, which has a lone pair in its outer shell, and they do that for stability. Alright, it's very, very rare to find in nature an atom that has one free electron. Alright, when you have one free electron orbiting around an atom, it is very, very reactive. Now, when it comes to it, in the HSC course, you don't specifically need to know the structure of an initiator, and generally what we're going to do in this first step of a free radical polymerisation is represent an initiator as a capital I. That was a little mistake just then. I just pulled the slide halfway off the screen. Anywho, you didn't see that. Now, if we're going to represent, once again, if we're going to represent that initiator as an I, we'll represent it as an I, and we represent it as a radical. You represent a chemical species as a radical by drawing a dot beside the letter or the symbol we are using to represent the radical, halfway up, like I've done just here. And that symbolizes, that tells other chemists that that chemical species is a radical. Alright, it's a free radical, and that means that it has one free electron in its outer valence shell, and it tells us that that is a very reactive chemical species. It's shorthand to represent that. So we're visually, by using this symbol, we are telling people who read our work a lot of information. Alright, now I want to just reiterate, you don't specifically need to know the structure of initiators. We'll provide you with an example on the next slide from here, but I just want to reiterate, you need to be able to represent them, alright, and a capital I with a dot beside it is perfect to do that, but actually going through the structure of them, alright, that is something which I would expect a question in the final HSC exam to give you a significant amount of that information. You may still have to draw a structure that involves shorthand and I, but you won't be asked to draw an initiator. Now, that initiator will run into our first monomer in our growing polymer chain. Now, if we have a look at the reaction we have on this slide here, you can see we have our initiator, we have our blue I with the dot halfway up the side, and that is right beside a monomer that contains the double bond functional group And if you have a look at that, it looks very, very similar to ethene. Only difference is it has this mysterious R just here. Now, in a hydrocarbon, an R as a substituent attached to a carbon represents anything. The letter R is by itself is not found on the periodic table. And this is another shorthand that chemists use to represent anything that could possibly be attached to a carbon in a hydrocarbon. Now, in this example here, R could be another hydrogen, which would make our monomer into ethene, or it could be a chlorine, which would make it into vinyl chloride, or if we're going to use the more modern correct name for that monomer, instead of the older, more common name for it, chloroethane. Alright, so just remember, if you see an R on a hydrocarbon, that means that it could be anything. Now, what will happen in this first stage of free radical polymerization is our radical will come along, it will collide with our monomer, and it will open up that double bond, much in the same way as we've been looking at addition reactions to ethene. Now, what will happen is that double bond will open up, like so, and we will form, first off, a covalent bond between our initiator and that first carbon from the double bond, and a new free radical at the end of the growing chain. And as you can imagine, this leads right into our next step, propagation. Alright, but what we're going to do right now is we're going to take a little pause and let's take a look at the structure of initiators. Now, benzoyl peroxide is perhaps the most common initiator used in free radical polymerization. Now, this is an unstable molecule. It has a peroxide group right here in the middle. Alright, that is a covalent bond between two oxygen molecules, as you can see just here. Now that's very unstable. All we have to do is put a little bit of energy into this molecule, possibly by heating it up, or if we provide specific wavelengths of light that interact with that bond, that can cause this molecule to split in two, creating two radicals. Now, as you can imagine, this is a popular initiator because it creates two radicals, and it creates two fairly stable radicals that are easy to work with. Alright, and it happens at reasonable reaction conditions, which is why it's actually used commonly. Alright, I want to reiterate, you won't be expected to remember the structure of this initiator. You may be expected to work with it. Alright, I believe this picture here, this diagram here, is actually from a past HSC question. Alright, a multiple choice question. Alright, you may be expected to work with a diagram like this and recognize that it is an initiator. Alright, and you can do that simply by seeing the free radical groups forming in the formation of this radical group, but you're going to be given a significant amount of information. The main thing is when it comes to an initiator that you can represent an initiator by drawing an eye like this with a dot beside it to represent that it is a free radical initiator. That's the core thing to remember. Now, with our polymerization, just remember, just to reiterate, we have our first step, initiation, and that is where our free radical runs into our monomer group. Our monomer's double bond opens up, and we form our covalent bond to our free radical and a new radical group at the end of the chain. Now, what we have now is the beginnings of a chain. The next step in our journey to a long polymer chain is called propagation, and this is where our growing chain, just here, runs into additional monomer units. And once again, those monomer units have a functional group, a double bond functional group, and that opens up, just like in the case, say, with the initiator. Alright, and that creates a growing chain, and as you can see with our growing chain, we have two repeating units now in our growing chain, and that will continue as more monomer units are available to the reaction. Now, one of the really fascinating things about polymerization reactions is they are very much like a recipe. And because there's this random element to these reactions where they're reliant on the collision of monomers with these growing chains, it is very common for commercial productions of these polymers to actually be a process where what they do is they limit the amount of monomer and slowly add it to the reaction in a very controlled fashion. In the business, this is called starving the monomer concentration. Alright, and they do that to carefully control the reaction. Now, once we have a propagating chain, the next step is termination. Now, termination of a free radical chain involves the free electron of the radical coming and colliding with a second free radical, which we can see is happening in this diagram here. We have two growing chains come together, and ideally that will happen as you'll end up with a nice long chain that is bound together by the formation of a covalent bond, as those two free electrons form a pair of electrons to form a covalent bond. Now, once again, because polymerization reactions, particularly free radical polymerization reactions, very much they follow this recipe-like structure in practice. It is actually quite common at the end of a polymerization reaction for the chemists involved to dose the reaction mixture with more initiator. They spike it with a small quantity of initiator, and they do that to react any remaining growing chains. Alright, what you'll actually find is as you're forming let's say you're doing a polymerization reaction in a beaker, as you're forming your growing chains, you can start running out of monomer groups. Alright, and it may be detrimental to your polymer to have unreacted growing chains in the structure, and so just to clean that up and to make it so your polymer is chemically resistant, what chemists often do is they often dose a polymer with a small amount of initiator to terminate it. So just remember that you could be terminating a chain by having it react with another initiator instead of another growing chain, in this case just here. Now, free radical polymerization has this really big downside. Alright, and that's if we look at the growing chain, as we can see in this diagram on the left here, alright, what actually is happening is as we have a growing chain, our radical can actually bend back around, and what it can do is grab a hydrogen from the chain and essentially steal the hydrogen and transfer the free radical to a different section of the chain. And that free radical will just continue to chug along as it comes into contact with more monomers, and will just continue off as a new chain, essentially a branch in the chain. Alright, and that can lead to polymer chains that can have all these little side branches coming off them. Alright, and having all these little side branches affects their physical properties. In fact, we often consider plastics to belong to two different classes. Low density plastic, which has a high degree of branching, and a good example of that is actually pictured just here, and many of you will have this material in your kitchens. But Glad wrap is actually often polyethylene or polypropylene. Alright, and they're often a low density form of those polymers, which is highly branched and readily forms a transparent film. Alright, but our story of polymers doesn't just end there. You can form straight chain polymers. Now you can do that by very, very tightly controlling free radical polymerization processes, but you still have some degree of branching. Or what you can do is you can use a catalyzed process to make your polymer chains. Now, I'm sure everyone's probably just taken a breath when we have moved to this slide, as this is a very complicated diagram. Now, we're talking about the ziegler-natta catalyzed polymerization process. This involves the reaction of a activated metal complex catalyst with our monomer units. And I'm happy to tell you that you do not need to know this process to the level of detail that is described in this diagram. It is, however, just a good diagram to illustrate this process. Now, we have our metal catalyst, alright, and that metal catalyst, it forms a what's known as an activated catalyst, so it's a chemical species that has to be carefully prepared. Alright, and as we bring that chemical species, as shown just here, into contact with monomer units, what it does is it forms this, the best way to describe it is like an end cap on the end of the chain. And as we start introducing new monomer units to that chain, the catalyst essentially can be viewed as an end cap that pops on and off the chain as it grows. Alright, which you can see in these later stages of the diagram just here. Alright, as we move to having 2 repeating units, that's symbolized by the little 2 right there, to having n repeating units, where n is a large number. And that creates a polymer chain. Now, the really cool thing about ziegler-natta catalyzed polymerization is that there is this super high degree of control of the growth of the polymer chain, and this can lead to very, very straight polymer chains that have very low, if not no, branching. Alright, which gives it some advantages over free radical polymerization, but those advantages, by comparison, they shape the physical properties of the material, so both processes do have their merits. Now, representing this, if you needed to talk about it, the core things you need to actually know is, one, the name of the process, the ziegler-natta catalyzed polymerization, and that the way the catalyst actually acts is as an end cap on the end of the growing chain. So if you had, what I would recommend you do is you draw it by you drawing a polymer chain, like so, and your catalyst as an end cap on the end. And what you can then do is represent monomers, free monomers, as small sections of chains. Alright, and they react by being passed onto the end of the chain here, and that creates a situation where this catalyst will actually pop off, just like the end of a soft drink bottle, and add the monomer chain in. And so our new chain, in this case here, would be our existing polymer chain, plus our monomer, and we would still have our catalyst end cap on the end of the chain. And so what you need to do, Year 12 students, is find ways to represent your catalyst using a diagram. Now remember, the level of detail you need to go into for the ziegler-natta process is very, very little. Alright, but you may, for example, be experiencing polymers. In fact, you actually are very likely to be experiencing plastics that have been made by this process. Now, with polymerization, there is a degree of randomness involved with the growth of chains. Alright, and so what that means is that polymer chains actually in a polymer will often be different lengths. Alright, and that's essentially recognition of the point that Both processes are reliant on the collision of material, and that can be affected by a range of factors. The position of people and equipment is a big one in a 3D space. Alright, and so you need to recognise that polymers will occur as a range. And one common way of viewing that is the number of polymer molecules versus the molecular weight. And so the diagram pictured here, it shows us that in our polymer, most of our polymer has a length, a molecular weight of this particular value, and on either side we have less of a percentage. Alright, but as you can see, with your distribution, you do have a bit of a tail towards higher molecular weights. Right, however, they are heading towards a particular maximum value. You still have this process even in catalysed polymers. It is just often a narrower distribution that is present. Now, we've talked a lot about two different ways in which polymers are manufactured. What we have not done is talk about some of the engineering processes that can happen to polymers after they are made. Now, one of the most very common processes, and engineering study students may already be aware of this process, is known as extrusion. And that is where you feed a thermosetting plastic. Alright, that is a plastic that can be reformed and moulded by heating it up into a barrel which has essentially a large screw in it. And what happens is that barrel will apply pressure and heat to our polymer. And polymer is often supplied by a manufacturer as small beads. Alright, it will apply heat and pressure to them and cause our material to align polymer chains. Essentially, if we take a look at our polymer, if we were to look at the chains, what you'll find is this polymer will enter this barrel kind of like a random orientation of chains. And when we melt it and we reform, we remold it in this process under high pressure, what happens is these chains can be aligned in straight lines. And what that can do is give us big advantages in terms of the design and manufacturing of plastics. There's a lot to it. This is one of those big questions, and right now what I have hoped to do is provided you with an introduction to this rather large topic. Thank you, Year 12. If you have any questions, please do not hesitate to ask me in class, or to leave a question in the comments below and I'll try to get back to you promptly. This is Mr. Nicholson, and this is another video prepared for Year 12 Chemistry. I do hope you've enjoyed it. I'll see you in class.